All right, so welcome to lecture 3. My name is Harmtedy. This is MSM 111. Yeah, so today we're going to look at sets. And to start with, we'll start by defining the sets and all other things that sets involve. And we'll also look at set operations and also the set algebra. Yeah, so let us begin. Let us see what we have for today. So today's lesson is very short. We're just going to look at, we're just going to spend most of our time to explain the definitions and everything. We want to understand sets in details. Uh, so we'll start with the same set. So this is just the outline of what we're going to look at today. Yeah, so a set by definition is a well-defined collection of distinct objects. It's a well-defined collection of distinct objects. Yeah. Then examples of sets we have, you can see here, sets can be denoted by these brackets here. Yeah. Then we can also denote a set using these brackets. We also have these curly brackets. Let me just explain something here because I want you guys to understand everything that we're going to be learning. So when you see these kinds of brackets, for instance, when you look at this one here, when you look at these kinds of brackets, it simply means that the elements inside, if you are told to count the elements inside, you just count them independently. So in short, in this first set here, what we have, we only have 3 elements in this set, not more than 3. Yes, but when you see these kinds of brackets, it means that we now begin to deal with real numbers. So when you're dealing with real numbers, then you find any of these 2 brackets, just not to say the numbers inside there, you cannot count them. They are infinite. No matter how good you are at mathematics, it's impossible for you to count the numbers between 1 and 2. Same applies to this other set here. No matter how good you are at mathematics, even a calculator cannot manage to calculate the numbers between 2 and 3 on this other one. So in short, anyway, we're going to learn about infinity and finite sets. Yeah. Let me just look at somebody here. Oh. Okay. All right. So what we're going to do is I'm going to send somebody saying the words are not clearly seen. So I'm going to send a slide. You're going to go through it on your spare time. Yeah, because if myself here I'm able to see them, then it simply means that maybe, I don't know, because myself here I'm seeing them very clearly. So maybe it's just something that has to do with maybe the internet or something. Yeah. Okay, let's proceed. But I'm going to send this slide. You're going to go through it on your own. Thank you for that question. All right, so we proceed. Yeah, we've looked at sets and I've talked about what these brackets mean. So when you look at these ones here, the first brackets here, when you have such brackets, just not to say 1 and 2 are not in this bracket, are not part of this set. When you have these square brackets, these they mean inclusive, meaning 2 and 3 inclusive. In short, 2 and 3 are part of the set. So when I write something like this, 1, and then I write a comma there, you have 3, then I write this. This simply means 1 is not part of the set, but 3 is part of the set. All right. So what is a null set? So a null set is simply, or is also called an empty set. It is a set that does not contain anything in it. It's symbolized by symbolized by this or a 0 which has been cancelled. Yeah, so today we're going to look mostly on the definitions and everything, so that tomorrow we just go into practical questions. All right, let's proceed. We have a singleton set. What is a singleton? Just from the word you can hear single. So singleton set is simply a set that has only one element. A set that only has one element is called a singleton set. Yeah. In other words, it's called a unit set. Unit simply means one. Singleton set, which is a single, meaning one element. Let's proceed. So an example of a singleton set is there. And sorry for putting that comma. I wasn't supposed to put this comma here. So when writing a singleton set, you just write one element inside there. Okay. Let us see how we can represent the sets. Sets are represented in various ways, in different ways. Actually, there are a lot of ways in which you can represent the sets. Yeah, a set, the denotation or sets are denoted by capital letters mostly, and then the elements are denoted by small letters. Yeah, this one I'm sure most of us know about this one. Yeah, so this is how you represent sets. You can just describe them. You can see here by description form, which simply means you can just describe. For instance, you have the set of vowels, in English alphabet. Yeah, and then the second set here we have is the set of all odd positive integers less than or equal to 15. And then the other set that we have is a set of all positive cube numbers less than 100. The other way we can represent sets is by set builder form. So when we say set builder form is simply these ways. For instance, when you want to represent this set in set builder notation, you are going to say x. These two dots means such that x. So in short, this is read as x is such that x is a vowel in the English alphabet. Yeah. And then the second set here can be read as x is such that x is an odd number and 0. So in short, you can write it this way or this way. Sorry, this and simply means this is one set. Or x is an odd number and it ranges from 0 to 15. And then 15 inclusive. So if you want to write this, you can also, anyway, I'll show you when you reach there. The third set here can be written as x is such that x is a cube number and 0 and it ranges from 0 to 100. Yeah, and then the roster form is the one that we all know, which is this one. You can see these are vowels from the alphabet, from the English alphabet. Yeah, and then these are numbers ranging from 0 to between 0 to 15. Yeah, in short, from 1 to 15. And then we have these cube numbers less than 100. Yeah, so this is how you represent sets. Let's try to look at finite and infinite sets. So today's lesson, as I earlier on said, it's a very short lesson. We're just going to look at definitions. I want you to go through these definitions so that even when we come and begin to do exercises and other work involving sets, it will not be a problem to us. It will not give us any problems. So today I'm not even giving you an exercise. I want you to have time to go through these notes, and then so that the next time we meet, but tomorrow maybe, go through these notes today and tomorrow, and then probably on Saturday, so I may give you an exercise from the notes, and then when you answer them, yeah, I'll see if we should proceed to the practical questions on sets or not, because we also need to look at De Morgan's laws. Okay, so let us look at a finite set. So a finite set is simply a set that has countable or finite number of elements. Yeah, this is what I've just written here. And then an infinite set is just opposite of the finite set. So the opposite of the finite set is just a set that is that has an infinite or uncountable number of elements in it. Okay, you can see that. So let's take a look at some of the examples of infinite and finite sets. Yeah, these are the examples that we have. So when you look at this set, this one is infinite. Why? Because it has these three dots this side. When you look at these three dots this side, they are simply showing you to say uh, the numbers are still going to the negatives, and they are not ending, they're just going to the negative side of the number line. So yeah, this is it. All right, so even the second one here is infinite because it's showing us to say the numbers are still going to the positive side of the what number line. Yeah, and then when you look at this one, the reason why this one is a finite set is because we have been told to say the numbers are ranging from 0 to 10, and then when you look at this is a set builder notation. We're saying x is a member of whole numbers which ranges from 0 to 10, meaning you can count the numbers between 0 and 10, which are whole numbers. It's just 1, 2, 3, 4, 5, 6, 7, 8, 9. That's so. Those are the numbers that are part of this set. And then when you look at this one here, x is a member of real numbers such that x minus 2 is equal to 10. This one is also a finite set. Why do I say it's a finite set? It's simply because when you simplify this equation here, you're going to have x. Let me just simplify it quickly here. We have something like this: x minus 2 is equal to 10. X minus 2 is equal to 10. So when you take this to that side, you are going to have x being equal to, this is 10 plus 2 there, you get 12. So in short, this set is saying x is a member of real numbers where x minus 2 is equal to 10. So meaning the value of x there is definite. Let me just delete this. Okay. So meaning the value of x there is definite, is just 12. Yeah, and you can count 12. 12 is just one number. So this one is also a finite set. Yes, now let us look at this one. Why do we say this one is an infinite set? When you try to do this, let me just do that. When you try to get this one and solve it, you have x plus 4 being greater than 12. So what you do is you take this 4 to the other side of the equal sign. You have x being equal to, oh sorry, x is less than, sorry, this is less than, not greater than. So x is equal to 2, is less than 12. Then you have minus 4, like that. So meaning your value of x is less than 12 minus 4, you get your answer to be 8. So now, what this simply means is that, and then in short here, we've been told to say x is a member of real numbers. So x is a member of real numbers. This means this can also be written as this one. Since we're talking about real numbers, remember what I said on the previous slide here, on this slide here. I said when you see these kinds of sets, just know that you're dealing with real numbers. So this is what is just here. Okay, so we're dealing with real numbers here. So in short, if they tell us to say x is less than 8, we can also write it as this. Then we put a negative infinity here, and then we say comma, we put 8 there. and then we use these brackets. So meaning it's impossible for you to count the numbers between negative infinity and 8, which implies that this is an infinite set. Okay, let us proceed. Oh wow, let us now look at the universal set. What is the universal set? The universal set is simply just a set that you come up with after combining different kinds of sets. Yeah. A universal set is a set which contains all the elements or objects of other sets, including its own elements. Yeah. So mean including if it has what elements. When you get, let's take for instance, okay, let me just get the same example which I wrote here. It's saying, yeah, it's usually denoted by U, but U is not the only letter that we use to denote the universal set. You can use any other letter. Yes. And what you should know is that there is no formula in the world that you can use to find the universal set. There is no formula, it doesn't exist. So meaning you deal with such a set by using inspection method. You just inspect. Yes, so let us look at this example here, which says, suppose set A consists of all element, or sorry, all even numbers such that A is equal to 2, 4, 6, 8, 10, and it continues to go. These three dots here means we are still going to the positive side. And and set B consists of all odd numbers such that B is equal to 1, 3, 5, 7, 9. So for us to find the universal set, we just need to combine this set and this set. Then we are done. And how is it going to look? To look like this. So this is our universal set. This is our universal set. All right. This is our universal set. Let us proceed. What is a power set? A power set is simply a set of all subsets of a given set. Yeah, I think that's the simplest definition. It's a set that is formed when you combine all subsets of a given set, sorry. So what happens is that when you are writing subsets of any given set, you also include itself. If let's take for instance, you are dealing with set A, and then you want to write the subset, subsets of set A. So you can even begin with set A itself, and please don't forget to add a what? Don't forget to add what's this? An empty set when you're writing the subsets. So meaning itself, the set itself, and an empty set are part of the subset of that given set. And then apart from that, you all right, let's proceed first. I'll explain other things. Yeah, for instance, here you've been given to say if set A is equal to this, yes, then all the subsets of this set are, you list them independently, then you begin to pair them 2 by 2. Don't repeat the same ones 2 times, you just write them once, and then this is the original set. The set itself is also part of its subsets, and the empty set. So these are the elements of the power set. Yeah. So this is a power set of A. And then when you look at P of A, simply means that P of A simply means that the power set of A. Yeah. So it's as simple as that. Okay. Let us now look at equivalent and equal sets. I'm sure after this maybe we're even done, because these are the only definitions that are on sets. Yeah, there may be other definitions, but these are the most important definitions for your level. Yeah. So the two sets, I'm just going to read through these notes, and then I'll be explaining where I need to explain. Yeah. So when you talk of when you talk of when you talk about the equality of sets, or in other words, when you talk about equal sets, we're simply talking about the set. Okay, let's take for instance, we have two sets A and B, and these sets can be equal only if the elements of set A is also the element of set B. Also, if two sets are the subsets of each other, they are said to be equal. This is represented by A is equal to B. Yeah, so when you have A being a subset of B or B being a subset of A, it simply means that A is equal to B. So if the condition discussed above is not met, then the sets are said to be unequal. This is represented by A is not equal to B. Yeah. So let me just read through equivalent as well, and then I'll explain the difference between the two. Yeah, so to be equivalent, the sets should have the same cardinality. Yeah, so somebody I'm sure is asking themselves to say, what is this cardinality? Cardinality is nothing but the number of elements in the set. Yeah, so a cardinality of any given set is just the number of elements of or rather in that set. So this means that there should be one-to-one correspondence between elements of both the sets. Here, one-to-one correspondence means for each element in set A, there exists an element in set B till the sets gets what exhausted. So here what they simply means is that, what this statement here simply means is that when you're talking about equivalent sets, when two sets are said to be equivalent, it simply means that they have the same number of elements in them. So despite them having different elements, they also have the same number of elements. Yeah. But when you talk about equal sets, yeah, when you talk about equal sets, let's take for instance, you have A and B. So when you have A like this, we have 1, 2 in A. Then we have 1, 2, like that. These two sets are equal. Why do I say so? Because the elements inside them are the same. And then these two sets are also equivalent. Why? Because they have the same number of elements. Let us now look at these two sets. We have A, which is equal to the small letter A, we have small letter B, and then we have C. Okay, like this. And then we have set B here, which is equal to 1, we have 2, we have 3. Yeah, so these two sets are not equal, but they are equivalent. Yes, so that's the way it is. When we talk about equivalent sets, we're just talking about the number of elements in those given sets. So since the number of elements in set A are the same as the number of elements in set B, then we say the two sets are what? Are equivalent. But if the sets, if the elements that are in set A are not equal to the elements that are in set B, meaning the sets are not equal. When you talk about equal sets, we are talking about everything in the set being the same. And then when we talk about equivalent, we're talking about everything in the set, whether different or the same, but the only key there is just having the number of elements inside there to be equal. Yeah. So this is what this statement here is talking about. The number of elements in A are equal to the number of elements in B, which is just the same as saying the cardinality of A and the cardinality of B are the same. Then we're talking about equivalent sets. So what if maybe you've been given a question? You've been given a question to say, find the cardinality of the power set of A. Find the cardinality of the power set of A. Let me write it this way. I'll use square brackets outside here. Yes. So how do you find the solution for this one? We're talking about this A here. Yeah. How do you find the solution of this? So cardinality is just given by 2 to the power. The cardinality of a power set is just given by 2 to the power n. So in short, how many elements do we have there? We have 3 elements in this set A. So you just say 2 to the power 2, which gives you, oh sorry, we have 3 here. Of 3 elements there, which gives you 8 as your answer. So the cardinality of the power set of A is just 8 there. So if you are to list the subsets of this set A here, you're going to have 8 8 elements in that set, which is the power set of set A. Hope we have no questions. I don't know if you have any questions, you can ask. This is what I prepared for today. I want us first to go through these notes, you understand them. Once you just understand them, it will be easier for us to solve questions on sets. The next lecture that we're going to have, it is just solving questions about sets throughout. We just solve a lot of questions there, and I'll give you the exercise. I'll give you some work that you are going to do and submit. And it's unfortunate that there are some guys who did not manage to solve the questions that I gave you as an exercise. So please, you should be making sure that you solve the exercises that I'm giving you. They are helping me to know whether you're understanding or not. Yeah, and most of them that submitted, they submitted quite impressive answers. Yeah, most of them got all the questions correct. So please make sure that you are submitting the questions as early as possible so that I also have time to mark. Yeah, either way, if you didn't submit, you can still submit exercise 1, but please make sure that you go through this lecture. You go through this lecture slide, you read all the notes that are here, understand them, so that the next time we're going to be solving questions, it will just be a walkover. You'll not have questions. You'll not remain stuck on anything. At least you know what it means. When I say let us find the cardinality of the power set of this given set, we do that. So what we're going to start with in the next lecture that we're going to have, we're going to start with De Morgan's laws of sets. We would do De Morgan's laws. After doing De Morgan's laws, we're going to start proving and showing, and we're going to start applying, in short, De Morgan's law. We're going to start applying De Morgan's law. We solve different kinds of questions. Yeah. After solving questions, and we'll call it, we'll mark the end of the sets. Yeah. And then we start another topic. We'll see what is going to follow. So please make sure that you go through the notes, understand them, and then we will come and do questions next week. If you have any questions in this last 8 minutes, please, you can ask. If you have any questions, you can ask from what we have learned. Okay, seems people have understood. All right, thank you very much for attending the lesson. See you in the next lesson. We're going to have our next lesson on Monday. Yeah, but I think before Monday, I'm going to send an exercise in the WhatsApp group that you'll be required to solve. Yeah, I'll just send that exercise based on the notes that we've learned today. All right, good night.